So we're going to go through the heart year 12. A lot of people struggle with these pressure graphs. So I'm just going to go through a few tips of how to interpret them. It's quite a nice one, is this, because not only has it got the left side of the heart shown, it's also got the right side of the heart shown. It's the same time scale. It's the same y-axis as well. You can see that the pressure in the right side of the heart is way less. It's far less muscular. And I've got all these intersecting lines, and it's quite easy to kind of get confused between the lines. So the first thing I do when I get a question like this is I sketch somewhere on the paper a quick heart. Yeah, so my quick heart always looks like that. So there's my quick heart diagram, and I know that this is because I get this wrong all the time, that's the left side, that's the right side. This is more muscular, so I always put that in. This is the left atrium, this is the left ventricle, and I'm just going to zoom in a bit further, so it's getting a bit small. And then this is the right ventricle and right atrium. And then I know that out of the left ventricle comes the aorta, and it needs to be sending oxygenated blood, so it must come back from the lungs, so it's the pulmonary veins, because veins come towards the heart. And here's my vena cava bringing blood into there, and this is the pulmonary artery leaving. I also have to get my valves correct. So this one here between the atrium and ventricle, that's our AV valve. I'm not going to bother with bicuspid, tricuspid, mitral valves and all that. It gets stick to atrioventricular valves, and then this here, that's our semilunar valve. And it's the same on the other side as well. Whenever we talk about valves, we're always interested in when they open, when they close, and it's important to give both sides of the pressure difference. So I will say that the pressure in X is greater than the pressure in Y, and you have to mention those sides. And I'm talking about chambers. When the pressure in the left atrium is higher than the pressure in the left ventricle, then that will force the atrioventricular valve open. Yeah, so you just have to give both sides of the pressure equation. So let's have a look at this graph and let's label it up, because again I've got these three intersecting lines. I always like to, in the exam, I'd get my highlighter pen out and just like kind of go over some of them. So let's just go over that one there. Yeah, just so I can make sure it's different to this blue one there. I'll leave the one not coloured in. But yeah, so it helps me just kind of make sense of the lines. So this, the highly variable one, which they ask you to label in the exam, this is the ventricle. Okay, and then the one above it is the aorta, and therefore this dashed line down here, that's the atrium. And I could put left in front of all of these. Again, look, the pressure gets way higher in the left side than the right side. However, they are still in sync. Look at that point here where it hits zero, it's the same as here. When it reaches peak, it's there. When it reaches peak, it's here. They're in sync. Okay, so that's really important. And I could highlight this one as well, but it's a bit more squashy down. But my solid black line is the ventricle again. It's the atrium, but it's the right atrium this time. And the dash line, sorry, that's going to be the pulmonary artery. Why is the pressure so much less on the right side of the heart? Well, it's less muscular. It therefore generates less pressure. And it needs to generate less pressure because it's pumping blood through fewer blood vessels. I would ignore the further problem. So if I think that there's the heart, here's the lungs, this is the rest of the body, and it's going to pump blood out to the lungs, back to the heart, and it's going to go from the heart to the rest of the body and back again. Okay, so if I say distance, well, there might be the heart pumps blood from itself to itself via the coronary artery. So that's a very small distance, isn't it? Yeah, if it's pumping from itself to itself, whereas and it's further from the heart to the lungs and back again. But it's the fact that there's branching blood vessels. So there's just miles more. I would talk about resistance. There's more blood vessels or more resistance is higher. Yeah, more friction. So it has to overcome that resistance or friction, therefore it has to pump further in total. So let's go back to this graph and put the valves on. So let's take this one here. So it's always where lines cross. So there's a cross point here. And that's when the pressure in the ventricle starts to exceed the pressure in the atrium. Yeah, I've already identified the lines. So I'm talking about the AV valve. I identified the valve first of all. It's the one between those two. So it's this one here. I've already done it on my little diagram. And this is when pressure in the ventricle exceeds the atrium. Well, that's going to close that valve. It's going to stop it going backwards. So that's closes. And then I don't have to think about this point. This is the comparable point over here. So this is when AV opens. I don't even have to think it through. They must be opposites. And then up here, when the pressure, so this is the semilunar valve. And this is when the pressure in the ventricle exceeds the pressure in the aorta. And therefore, that's going to cause it to open because blood's going to want to leave. And here, this is the SL closes. So I would put that onto my diagram to start with, because questions are going to ask about this. They tend to ask about, when do valves open, when they close, for how long does blood leave the heart, etc., etc. And you can think it goes in order of time: closes, open, closes, open. So there's ways of checking it. So yes, so for how long? Let's go through. So for how long in the cardiac cycle is the ventricle contracting, or how long is ventricular systole? So ventricular systole, some people call it systole. Systole equals, well, that's when the ventricle contracts. So that's going to be from when the AV valve closes. So that's here. And then when it stops contracting, that's when we get this sudden drop off. So that's going to be there. So it's in 0.1s of seconds, 0.1, 0.2, yeah, so 0.3 of a second. That's ventricular systole. People confuse this because you see that the pressure is increasing in the ventricle here. It's increasing. It's still less than the pressure in the aorta. Therefore, blood isn't leaving the heart. It's just building up pressure. Then the valve opens, blood squirts out. It's squirting out, but there's less blood to squirt out, and therefore it tends to fall off a bit. And then the ventricle relaxes, and you get this massive drop off in pressure. Okay, so 0.3 of a second. How long is blood leaving the heart? Well, that's just between the valves, though. So that's going to be about 0.25 of a second is blood actually leaving the heart. Okay, so you have to be reasonably careful with these graphs. Again, people confuse this, thinking blood's going to be leaving for all of that time. It's not, because pressure has to build up first, because the pressure in the ventricle has to exceed the pressure in the aorta, and the aorta is always at a high pressure. You've probably heard about blood pressure measurements. Here we're using kilopascals, but if you go to your doctors, they'll measure it in millimeters of mercury. Hg is mercury, like a height of mercury. Yeah. And they give like 2 pressure readings, and it's going to be something in the region of, let me think, like 120 over 80 is the kind of like normal blood pressure average, but like no one's average, are they? But anyway, so 120 would be the peak pressure during ventricular systole, and the 80 is the pressure of the blood vessel, of the artery anyway. So, like the aorta, when it's at low pressure, it's running at 80. When it gets this surge of blood, it boosts it up to 120. Right, so that's it. Just one other thing they ask about this is what's the heart rate for this? Well, I've got one cardiac cycle. Sometimes it gives you it kind of gives you a few of these, and you have to pick out where you get the repeating pattern. So you have to be a bit more careful on that. But here I've just got one cycle, and therefore it's gone to zero, and then by here it's gone back to zero. So the heart rate is in beats per minute. So we just write, well, this is in seconds. So there's 60 seconds in a minute, and my cycle is 0.8 of a second. Therefore, my heart rate is 75 BPM. Sensible answer. Again, sometimes they don't give you a human. It could be a little shrew or something, in which case you can expect far higher beats per minute. But that's about it for these pressure graphs. So yeah, top tip number one: draw a little heart out. If you can't draw a quick heart out in like 10 seconds, it's something to practice, and then relate it to this. And yeah, people forget that the sides of the heart have to be in sync. But yeah, the right side of the heart runs at far lower pressure. Its muscular wall is far less, and therefore it can generate less pressure. But then it's only pumping blood, to one organ, whereas the left side is pumping blood to many organs. Hence, there's more resistance. Nearly there. I'm trying to keep these under like 15 minutes. So let's just have a. So we should be okay if we just have a look at this. So this is like a table version of the same thing. There's 3 marks on offer. So let's have a look through. So yeah, the table shows the volume of blood in a man's right ventricle at different times during one cardiac cycle. So yeah, so I'm going from 125 up to 148, and then down, and then back up again. So it's kind of doing over time. It's going up, down, and up again. Use a table to calculate the man's heart rate in beats per minute. Right, well, I have to find one cycle. It's told me it's one cycle. This is when people overthink this and think, all right, 0.1 point, all right, so that's 0.8 of a second. Yeah, but it's like it's this cardiac cycle is 0.7 of a second, as it takes 0.1 of a second to get to 148. So that's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Yeah, so it's one cycle. If I went from my graph, the time taken from the peak to the peak would be 0.7 of a second. So it's 60 divided by 0.7, and you can think that you're wrong because it's going to give me a decimal. So yeah, that's 85.7 beats per minute. Then it wants us to get to the cardiac output. Again, we just learn this. That's stroke volume multiplied by heart rate. I now need my stroke volume. So that's the volume of blood that leaves the heart from a ventricle. So if we just quickly go back to that previous graph, yeah, this is showing pressure. If this was volume instead, volume in right side, volume in left side, they would be identical. The left and right side have identical volumes, unless you've got a heart issue. So yeah, the left and right here, you won't get any real difference. It'd be the same answer. So I need my stroke volume. So what volume of blood is leaving the heart? It's 3 marks, so it's going to be more complicated than just one multiplying 2 numbers together. So yeah, so I get it goes. My maximum is 148. However, the ventricle never fully empties. It's like I can't empty a tube of toothpaste. There's always something left in it. And our tube of toothpaste here is 55, so I just minus them. So I get my difference. All right, so that's 93 centimeters cubed. The answer, it wants it in centimeters cubed per minute, so it's kind. Sometimes it's, the SI unit for this is decimeters cubed per minute. And the decimeter cubed, that's 1,000 centimeters cubed. So the actual volume of this ventricle, I'm a nightmare for dividing by 1,000. So I always lose a decimal place. Yeah, so the actual volume of the ventricle is 0.093 decimeters cubed. However, it wants it in centimeters cubed, so it's nice and easy. So I just multiply these two numbers together, and that comes into 7971.4 centimeters cubed per minute. If I times 85.7 by 93, I don't get this, but that's because this is rounded to one decimal place, so I kept it nice and raw in my calculator so that I give the correct answer. So yeah, so it's just being careful. You can see why we want to use decimeter cube, because if it's what's the um, you know it'd be easier to say that it's 0.093 multiplied by 85.7. Yeah, so so saying it'd be 7.97 decimeters cubed per minute. It's just an easy number, but it wants it in centimeters cubed. Last thing, just to say on here, I've gone on my 15 minutes, but never mind. Mammals, we can vary that slightly, so we can make a small change to that, or stroke volume, how much blood comes out. So the heart can kind of like have a bigger pump, but we change our cardiac output mainly by changing the heart rate. Yeah, so large change. I can change mine from it can go as low as like 50, and it can go up to, well, it's 220 minus age. So I'm in the 180 mark kind of area. Yeah, so you can get a massive change here, whereas the stroke volume doesn't change a great deal. So I'm going to finish there. Hopefully there was something useful. Take care.